Hello again. Here, let's continue with our very interesting new chapter, chapter 13, chemical kinetics. We started from chapter 14 on Julia's textbook, and then we go back to chapter 13. We are moving around the chapters, and I organize that way to follow a sequence, and that sequence matches the sequence of labs we are presenting to you. Let's start our section today with another quote from Albert Einstein. Number 2, perseverance is priceless. He said, it's not that I am so smart. It's just that I stay with problems longer. That statement has a lot of truth. In science, we face problems all the time. Science is a way to live with problems all the time. A way of living with problems. But our motto is to solve problems. And that is what keeps science alive. That's why sometimes we say we love to solve problems. All right, so let's start with our new chapter. I love this chapter. It's really, really interesting. Applications and the theory and the concepts. It's really interesting, and I hope you will love it too. So here, I'm going to start with a little introduction on this chapter. What is kinetics for you? When we hear the word kinetics, what comes to your mind? Yes, some of you are thinking on movement. Something that is on motion. And that is what we're going to do in chemistry. We're going to read the speeds of reactions. Kinetics is the part of the chemistry that studies the speed of reactions, how fast reactions work. And now we're going to solve a lot of problems here. We are going to apply a lot of math in this chapter. Probably this is the one of the chapters that apply more math. So we need a lot of your math skills. For that purpose, I will recommend go back and review a few concepts. I'll show you what I want you to review. I will suggest you go and review, let's say, logs. So you go logs, review. this, here is my marker. All right, so we had logs. Review logs base 10 and also natural logs. This is base E. This is 10 to the x, and this is e to the x. Number E for natural logs. So we are going to use these two concepts from now on during the whole, the rest of the course. Logs here, logs there, logs base 10, and natural logs. Many applications for our chemistry purpose. Please go review what is the meaning of this, and also properties of these logs. Properties, and also operations. How to operate logs. Like, for example, we are going to use plus. This is not T. It's not a T. It's a plus sign there. It's a plus. My eraser has a little delay too. Eventually it's going to erase that. It's not doing it. All right. Let's not waste time over there. So I'm going to write everything. Plus and subtraction. Multiplication and division. This for operation. That's it. You don't need more operations there. How to operate with logs. So we need that. That's essential from this chapter on. So you don't want to suffer while I'm talking about this and on how to proceed with this, because most of the calculations, remember, you need to do it yourself. I'll show you how to do it, but you need to finish it. The next one, simple exponential operations. Please work out properties of exponents, 10 to the a, and operations like addition, subtraction, multiplication, right? Like, for example, how to do 10 to the a or 10 to the b, 10 to the a plus 10 to the v. Operations, basic operations, those are the most basic operations. 10 to the a times 10 to the v. Fractions also. Fractions are very important, and we are going to use those a lot. All right. So I recommend you, please stop the video now, stop the recording, and do the search. Very quick research. Read a little bit of this. You don't have to spend a lot of time doing this. Take your notes, write it on memory cards, and have it ready for you to use later. So, what is the hint for problem solving strategies? It says, if you practice, and practice, you will improve your skills. So how do you improve skills? Practicing and practice and practice and practice. I give you 2 links here. You can write this down on your browser and it shows how important is practicing whatever you want to master in order to improve yourself. All right, let's go to subject, kinetics. Again, chemical kinetics measures the speed of the reaction. We can measure the speed of the reaction in 2 ways. We can measure the speed of the reactants disappearing. So we have the reaction here, the reaction A plus B forming products. This time, notice that we have a reactive A plus B making products. And this is going to be our generic reaction we are going to use many times during this chapter. A moles of A plus B moles of B to form products. Notice the intentionally I haven't written the products like I did on the previous chapter. In the previous chapter, we described the products as C and D. This time I'm not writing those, I'm just writing products because really we are going to focus more on reactives here, describing the properties of A and B. You will understand that as I go through the chapter and I explain a little bit more later. So we can measure the speed of the whole reaction just in terms of reactants disappearing, because when, as we wrote initially, I showed you this graph before, and we have concentrations here, and time here, and we have concentration of reactives somewhere here. Those are reactives. And what is the concentration of products? Concentration of products is here on 0. This is 0. 0 time, 0 concentration. So at 0 time, we have this initial concentration of reactives. And as time goes, we notice that, and you already know that, concentration of reactives A plus B starts to what? Increase or decrease? Decrease, right? So this starts to disappear. Concentration of this starts to disappear, to go down. And at the same time, concentration of products, concentration of these products here will start to show up. So it's a concentration of products. This is concentration of products. It starts to go up, to show up, to appear. Concentration appears. And what happened with the concentration of, concentration of reactives? This one, this is a concentration of A plus B. It starts to go down. And we say concentration disappears. So we can measure the speed at which reactives disappear. I forgot to write the B here. We can measure how fast concentration of A disappears. We can measure how fast concentration of B disappears. If you measure one of those, you can know what is the overall speed of the reaction. So you can measure only one, or you can measure it both, depending on the reaction, depending on your needs, depending on what you are doing with your chemical reaction. Similarly, you can measure the speed of the reaction, just measuring how fast product starts to show up, starts to appear. There are different ways to do that. Right, so we had two different ways to measure the speed of the reaction. In some reactions, it's a lot easier to measure concentration of products showing up. It's easier to measure that. So then you choose that. You choose the concentration of products, how concentration of the speed of the concentration of formation of products changes over the time. And you will use that to measure the whole, the speed of the reaction. Because probably it's easier to measure it here, and probably it's a little bit complicated from the experimental point of view. Some experiments are a lot easier probably to measure how fast concentration of B disappears. So you use that to measure the speed of the whole reaction. And we call this the overall reaction. This is the whole reaction. That's called the overall reaction. Sometimes in a particular reaction is a lot easier to measure how fast concentration of A disappears. So you use that to measure the whole speed. And that is what we call the rate of the reaction. And that's what we're going to do in this chapter. We are going to measure rates of reaction, speeds of reactions. Why is that important? Why in chemistry we want to know the speed of the reaction? Why we want to measure the rate of reactions? Because that gives us a lot of information about the reaction. For example, it can tell us how reactants change into products. How is that process going on at molecular level? And that will help us to find and to write or to propose a reaction mechanism. And we are going to do this. I'll show you how to do that. Using the information to propose reaction mechanisms or analyze reaction mechanisms, to prove reaction mechanisms. So in general, this is what we're going to do in this chapter. We're going to study reaction rates. I'll show you how to measure rates and how to express rates. Different rate laws. We are going to study different rate laws. So it will depend, the rate law depends on the concentration of reactants. Also, we are going to study integrated rate laws, and I'll show you how to calculate that over the time. The first one will help us to write reaction mechanisms. Integrated rate laws will help us to make predictions. So this one. Reaction. That will help us to find reaction mechanisms. And the second one will help us to make predictions. I'm not talking about predicting your future or somebody else's future. No, I cannot show you that. That's my secret. I'm talking about predictions in a chemical reaction. For example, if you start with X number of grams of reactive, you can predict how many grams of product you will make in 2 minutes, or in 2 hours, or in 3 days, or in few seconds. Few seconds later, how much you will get. Just by knowing the speed of the reaction and using integrated rate laws. We're going to study half-lives of chemical reactions. We're going to define what is half-life and applications of that. Especially very important when we're talking about half-lives of radioisotopes. And that's why the next chapter is going to be nuclear reactions. So this, I'm connecting this chapter with nuclear reaction, which is, I think it's chapter 22 in the textbook. It's one of the end chapters. And I brought it here next to this chapter, so that's going to be our next chapter, because they're related, because we are going to share the same integrated rate laws and same half-life formulas that we use in chemical kinetics. So they are related and they have that common ground. And then we are going to study Arrhenius equation. The Arrhenius equation will help us basically to find something that is really important. And we call it activation energy. And then we are going to spend some time, a little bit more time, talking about mechanisms, right? From here. That tool will help us to understand mechanisms and to write mechanisms. So this is what we're going to do in this chapter. Let's start with the reaction. All right. This is one example. I've been mentioning reaction mechanisms, And this is one example of reaction mechanism. Here, the first one, it shows a overall equation. It's generic one. This is the overall equation. You see 2A reacting with 1B2 in a reversible reaction to form 2AB. And we call that overall reaction. The overall reaction, usually the equations you have seen so far in Chem 11 and Chem 12 so far, they all were overall reactions because it shows the whole thing, just the reactives and the products. What is the initial material and what is the final material? That's it. Now, in this chapter, we are going to study what's going on at molecular level during that reaction. How A and B are working together to make AB. And we are going to describe the process showing the mechanism. And we use steps. So then we can figure out, using the Rayleigh laws, we can figure probably that during step 1, the reaction proceeds this way, and also we'll find that that's going to be the last step. And then during the second step, the reaction proceeds this way to finally get the product. So you see, we're breaking down into steps, and that is what we call reaction mechanism. And this can be found only and only through experimental. And this experimental result or proposal must match the integrated, the Rayleigh law for that reaction. I'll show you later how to do that. Okay, let's start using simple concepts, general concepts. There are 5 factors that affect the speed of the reactions. 5 important factors that affect the speed of the reaction. 1 is the chemical nature of reactants. Some reactions or some reactants by nature are very active. Like, for example, sodium. The reaction between sodium and water is a very fast reaction. If we compare the reaction of sodium with potassium, both sodium and potassium belongs to the first group of the periodic table. And we say that these metals are very active, very reactive, especially with water and oxygen. So potassium is more reactive than sodium, and sodium is more reactive than lithium. So the reactivity of these metals of the group 1 increases from top to bottom in that group. So that's their nature for these particular reactions. However, if you place the sodium in oil, there's no reaction there. They don't react. So they are very reactive depending on the conditions. They're very reactive. Sodium is very reactive with water and oxygen, but it's not reactive with oils. So the nature of the material is important. Another example, and those reactions goes fast. For example, the reaction of sodium and water is a very fast reaction and produces a lot of heat. So they are by nature fast reaction. We can compare with the reactivity of, for example, iron with water. How fast is that reaction? Iron and oxygen. So basically, iron doesn't react with water. It's not likely. The reaction is not likely. What about the reaction of iron and oxygen? Yes, it occurs. And what is the name of that reaction? Iron and oxygen? Iron solid plus O2 gas to form Fe2O3 solid. What is the name of this reaction? It's called oxidation. It's an oxidation reaction. Oxidation. Oxidation. Oops. Okay. Okay. It's an oxidation reaction. Oxidation. What is the other name for this reaction? It's called rusting. Usually your bike outdoors under the environment, raining, water, and oxygen, oxidation will occur. But that is a slow process. So this reaction is going to occur, but it's going to be very slow. A slow reaction compared to that of sodium solid plus O2 gas to form the oxide, the metal oxide. Solid. And to form peroxide too. It's very fast and explosive reaction. So you see, so the speed of the reaction depends also on nature of materials, nature of reactives. Some by nature are very reactive and they go through a very fast reactions. Others goes very slow. Like for example, the firework. firework uses materials that are very fast, that goes very fast. One of those is this. To form this oxide here, iron trioxide, that produces the nice red colors during the firework. The red colors that you see during the firework. As other metals can also produce that. Aluminum and oxygen also is a fast reaction. Zinc and oxygen very fast. The aluminum and oxygen produces the white color during the firework. TNT. What is that? Trinitroglycerin is an explosive. Plus O2 from CO2 plus water and nitrogen oxide and heat. And that is really fast. That's an explosion. What is an explosion? Explosion is just a very fast reaction, and that fast reaction produces a powerful sound wave. It moves a lot of energy, the sound moving very fast, moving a lot of energy that can destroy things. So, because it's very fast reaction, very fast expansion of gases produced during the oxidation. So it's a fast process. So you see now we see applications of the importance of knowing the speed of the reactions. Another factor that affects the speed of the reaction is the phase of the reactants. In what phase materials are reacting. For example, you have gases you have homogeneous reaction. In a homogeneous reaction, we have two situations for homogeneous reactions. Gases, so reactives are gases and forming products that are gases. Gas making gas. Or the other situation for homogeneous reaction is when you have aqueous. The most common, aqueous. You have reaction running on a aqueous environment in water. So those reactions goes relatively fast. They can run faster because it's direct molecular contact. There's more chances for collisions between particles, and once the particles collide effectively, they can react. And here are more chances of particles colliding because we have molecules moving at certain average kinetic energy, which is the temperature. So there are more chances of collision here, and so the reaction can go fast. Same thing for the aqueous. In aqueous, the water is providing a media for ions to work together, and also increases the chances of effective collision between ions or molecules also in the aqueous solutions. However, when we have heterogeneous, reaction. So that means we have, for example, solid plus gas. Now we are including another factor. This solid depends on how you presenting the solid in the reaction will affect the speed of the reaction. If you place a big chunk of solid to react with the gas, compare, for example, you put a junk piece of material, the reaction will go slower than if you break this into small pieces or smaller pieces. So what you're doing is increasing the surface area where the other reactive can effectively collide with these particles here. Collisions. More chances for collisions because you are increasing the surface area. Increasing the chances for direct contact between particles. So that's one way to increase also the speed of the reaction by increasing the surface area. Another factor that affects the speed of the reaction is the temperature. And that makes sense because if we have a system, let's say we have a system at temperature T, let's give a number, 25 degrees Celsius, a room temperature. You have another system at temperature 2, which is 60 degrees Celsius. For a particular reaction, these molecules have less kinetic energy than these molecules here. These molecules here are moving faster each other. So if they are moving faster, they have more chances, there's more frequency of collisions and more chances for effective collisions here. So the speed here increases. The speed of the reaction goes up at higher temperatures. Kinetically. So from kinetic point of view, the speed of the reaction increases. Later on, we are going to study more factors related to this concept, and we are going to talk about thermodynamic conditions. So from kinetic, and this is important to remember, from the kinetic point of view, increasing the heat, the temperature, increasing the average kinetic energy of molecules will increase the speed of the reaction. Now, from that thermodynamic point of view, we need to ask, is the reaction going to occur at higher temperatures? Interesting question. Will occur? Will the reaction occur when you increase temperature? So sometimes increasing temperature favors the kinetics, but not the thermodynamics. You will see that later when we study the thermodynamics. Another factor that affects the speed of the reaction is the presence of catalyst. So catalyst is a substance that changes the rate of chemical reaction without being consumed. So if we add a catalyst to a reaction, and you will see we have one lab and one demo. In one of our demos, we show a reaction that occurs with catalyst. That's the clock reaction with iodine. Without catalyst, that reaction usually goes at room temperature. Usually it takes 150 seconds at room temperature. The same reaction at room temperature with 2 drops of catalyst occurs in less than 2 seconds. That fast. So the catalyst affects the speed of the reaction. There are other type of chemicals that works like catalyst. They are called inhibitors. They work opposite. They speed down. So the catalyst increases the rate of the reaction. Whereas the inhibitors, they are catalysts, but in the opposite direction. They reduce the speed of the reaction. They slow down the reaction. This is important. For example, some inhibitors, they inhibit the combustion reaction. So if you add those inhibitors to the fabrics will slow down the combustion process. So it will not catch fire easy or easier. So for example, wood, you can add during the process of wood, they add inhibitors to, they are called also fire retardant. So this slowing down, they slow down the combustion reaction. In the biological systems, we all know about the enzymes. Enzymes are catalysts. They help to speed the biochemical reactions. Another factor that affects the speed of the reaction is the concentration. Concentration of reactives. So this factor affects both homogeneous and heterogeneous reactions. And we are going to spend time here because our rate law will be described in terms of concentrations. So what is a rate law? How do you express rate of the reaction? Rate, when you hear the word rate, is a ratio. It's the change of something over time. That's rate. So the denominator is time. Usually we use seconds to measure the rate. So how do you measure the rate of the reaction? If we have a reaction A plus B making products. So you can say the rate of the reaction. For example, if you choose to measure it based on the concentration of A, so you say the rate will be the change, delta stands for the change of concentration of A over the change of time. And what's happening during the reaction? What's happening with the concentration of A? During the reaction, the concentration of A is disappearing, is going down. As you can recall from the graph we just drew. So the rate, the numerical value of this will be negative. So the rates are negative of the reactants. And you can say, you can write similar expression. You can say, well, okay, you can measure the rate for the reaction in terms of change of concentration of B. So you say, okay, so the rate can be expressed as the change of concentration of B over the change of time. And this also, since B is being consumed, concentration of B is disappearing, that is negative. And the units, what are the units of rate? Units of rate are important. I repeat, units of rate are important. Therefore, we need to write the units of rate. In the last chapter, we were talking about equilibrium constant, and we said that equilibrium constant, we don't care about the rate, the units. The units are meaningless when you're talking about the equilibrium constant. And now, in this chapter, we are measuring rates, and they have units, and these units are important, and we need to write it down. So what are the units of rates? What is the unit of concentration? Molarity over time, which is seconds. So these are the units of rate. How can you express this? A different way to express this, you can say molar seconds -1. Two ways to represent the rate of the reaction of any particular compound, any particular reactive. Moles per second, that's how you read it, moles per, molar per second, sorry, molar per second, it's not moles, molar per second, or you can say is molar seconds -1. Or you can say here moles per second, but this is exactly the same thing. And remember, what is molarity? We can break this down. What is molarity? Molarity is moles of A over volume over seconds. Over liters, right? Liters here. Over liters, volume in liters. So moles per liter second, -1. So that's another way you can write it there. So it's going to be moles per liter seconds negative 1. Or you can write it moles, liters negative 1, seconds negative 1. Be aware of different ways to write it, because you can find this on the textbook, on the questions, on the test, different ways. And when you see this, you know that's a rate. When you see this, you know that's a rate. When you see this, you say, okay, that's a rate. Rates or reactants are negative. Notice that I'm not expressing here rates in terms of products, because initially when the reaction is happening, there are no products. And you want to know exactly what is the change initially, the change of concentration of your reactives initially. So by convention, the rates are expressed only in terms of reactives by convention. That doesn't mean we cannot measure it. We can measure the speed of formation of products, yes. But by convention, we want to express the speed of a particular reaction, overall reaction, we express it in terms of rates of reactives only. Another thing, by convention, we express the rate using positive numbers, even though the rate is negative because this concentration is going down. So by convention, we don't express the negative. You convert this into positive. So you use the absolute number. So you will see the rates as positive numbers. When we are solving equations, so sometimes you have to take into consideration and remember that the rate of reactants are going down. So don't forget that. If you make a calculation where the rate of the reactive is going up, is something wrong, right? Because the reactives are being consumed and the concentration goes down. Another way to express this, for example, when you say the rate of the reaction equals negative delta concentration of A over delta time. So the derivative of this, you can say D using lowercase d, the concentration of A over dt. That expresses also the change. This little symbol here is the derivative and represent the change also. So either way, this is negative. So this represents more like mathematical operation. The change of this concentration as function of time, depending on time. And there are different rules to solve for these mathematical operations. And that's what we have here. Concentration, again, can be expressed in different ways. Let me give you, now, there's another situation. What about the stoichiometry of the reaction? What happened with the stoichiometry of the reaction? So let's say this one here. So the relationship of the stoichiometric coefficients, I just lost my slide here. Let's move this here. Okay, where's the bar? There you go. Okay. The relationship between the stoichiometric coefficients in a balanced chemical equation and the rate expressions is here. So we can relate the individual rates of reactives and products. And here is how you do it. A and B are reactives, C and D are products. So reactives disappear, concentration of reactive disappear over the time. And concentration of products appears over the time. So that's why these rates are negative, because they are going down. And here we have the stoichiometric coefficients. For products, since concentration is increasing over the time, then these rates are positive. And here are the stoichiometric coefficients. So yes, we can relate the rates each other. Very important if the problem tells the rate of disappearance of B and ask for the concentration of D after certain period of time. So you only need to relate these two and you say, okay, so concentration minus 1 over stoichiometric coefficient of B is 1 over B times concentration of B over time change is equal. This product is forming, so it's going to be positive 1 over the stoichiometric coefficient of D times concentration of change of concentration of D over change of time. So here you relate these two. Let's apply that. We have one example here. Well, let me see my example. I lost it. All right, so seems like I lost the example, but I have another one here. I don't know what happened with the one I had it ready. Okay. This is another example. And shows the graph of concentration over the time of the reaction here. And notice that the curve represents how concentration of reactive is disappearing over the time. It's going down. From there, we can calculate the instantaneous rate of the reaction. That means the rate at any specific time. And that will be the tangent of the reaction rate curve at that particular time. So at this moment, instantaneous speed, which is the tangent to that, will be the change of this concentration here, which is, we measure it from here to there, will be negative 0.027 moles per liter. That's the difference of concentration from this point to this point. And it's negative because it went down. Concentration went down from 0.07 to 0.04. And that happens in a period of 110 seconds. So if we divide the change of that concentration over the period of time, we get the rate to be 0.00025 moles per liter per second. Or moles, liters -1, seconds -1. We need to express this in scientific notation, so the rate will be 2.5 times 10 to the -4 moles, liters -1, seconds -1. So, in general, we need to express the rate of the reaction, and we express the rate of the reaction using something that we call the rate law. This is the most important law you will learn today. Rate law for any reaction. Now that we already know how to write rates of reactions with respect to any reactive product, now we can write the rate law, or to express the rate law for a reaction. So our reaction is A plus B. This is our genetic reaction, making products. So again, by convention, we are going to express the rate law in terms of disappearance of A and disappearance of B only. We are not going to express rate laws in terms of products. By convention, that's the way we are supposed to write rate laws. So you say the rate law for that reaction equals, and this is a law. This is a law, so it's going to be that way. Every time you express the rate law, you need to do it this way. So the rate for that reaction for the overall reaction equals a constant lowercase k, which is called the rate constant. This is going to be, is called the rate constant, times concentration of A elevated to a exponent, and we're going to call that exponent M, times the concentration of B elevated to a exponent lowercase n. M and n represent any number. So there are a few things to analyze here in this Rayleigh law. Let's describe the parts of the Rayleigh law. First, we have a constant. It's called a rate constant. Notice that this is a lowercase constant. This is a different constant that has nothing to do with the equilibrium constant. We are not talking about equilibrium. We're talking about rate. So this is called the rate constant. And the rate constant has units. And these units are important, and we need to write the units of the rate constant every time. Also, notice that we have exponents. Yeah. On this expression, we have exponent M and the exponent N. M and N. M as a Mary and N as a Nancy. Two different exponents. And we call these exponents, they are called the order of the reaction. Orders of the reaction. So we said the orders of the reaction are M and N. And we say M as a Maury is the order of the reaction with respect to A. Concentration of A. And N as a Nancy is the order of the reaction with respect to B. Concentration of B. So that's how you express that. So they are individual orders, M with respect to A and N with respect to B. But also, when we add M plus N, that is going to give you something that we call the overall order of the reaction. M plus N gives you the overall order of the reaction. Another important fact about this Rayleigh law is that M and N can be obtained experimentally. So you need to do the experiment. You need to actually run the experiment with the reaction, changing some variables during the process to find experimentally the value of M and N. And that is one of our next labs. In a couple of weeks, maybe next week, we'll show you the demonstration of the kinetics experiment where you will need to find the order of the reaction experimentally. We run the experiment, we take measurements, we take times, we measure concentrations, we graph the information, we follow the protocol instructions, the handout instructions, we graph all the data, and we can find experimentally the values of M and N for that particular reaction. And those are the orders of the reaction. But you need to remember, the only way you can get those numbers, these exponents, and therefore the overall order of the reaction is through experiment only. We need to say this to make emphasis on the fact that stoichiometric coefficients of the reaction has nothing to do with these orders. We didn't even write the stoichiometric coefficients in this equation. Look, no stoichiometric coefficients. You can write it. Look, I want to write the stoichiometric coefficients, right? Let me write it so just to make emphasis on that situation. What is the stoichiometric coefficient for A to balance it is lowercase a. What is the stoichiometric coefficient for B is lowercase b. And notice that the orders of this reaction with respect to A and B have nothing to do with the stoichiometric coefficient. So you cannot assume that the exponent here comes from here. No. Those are the stoichiometric coefficients used to balance the chemical equation, and these two numbers were found through the actual experiment. This is experimental data. I had to repeat that many times because it is a really important concept, and you will learn how to find these exponents. We have an actual lab to do it here. I'll show you how to work with these orders and what information you can get from these numbers, from the order of the reaction. So let's see one example here. Look this example. For this particular reaction, it is balanced already. Some species are in the ionic form. And I believe all these are in the aqueous solution. Except for this one here, which is a solid. So we have aqueous species. But notice that this is a solid and this is a product. So we don't care because we are going to write the Rayleigh law as function of the concentration of reactives only. So it says from experiment, the rate law for that reaction is rate equals rate constant times concentration of H2SeO3 to the first power times concentration of I minus to the third power times concentration of H plus to the second power. So, and also at 0 degrees Celsius, they calculated the rate law for that. So look the expression of the rate law and notice that the stoichiometric coefficient has nothing to do with the exponents. The order of the reaction has nothing to do with the stoichiometric coefficients of the balance reaction. This is called the overall reaction. Here, the stoichiometric coefficient here is 1, and happens that the order is 1 here for the same compound. But that is because that was the experimental result, not because we are using this 1 from here. For I minus, look, the order is 3, even though the stoichiometric coefficient is 6. So again, these numbers have nothing to do with the stoichiometric coefficients in the balanced chemical equation. How do you read this? According with this experimental rate law, this reaction is first order with respect to the concentration of this compound. That's the meaning of this exponent. That's the order. You say it's first order. You don't say order 1. You say first order, because orders can be first, 0 order, first order, second order, or third order. You also say that the reaction, the whole reaction also is third order with respect to I minus. Or you can say also the reaction is second order with respect to the concentration of H plus. That is the meaning of that rate law. That's how you read it. So you say the reaction, the whole reaction, is first order with respect to this compound, is third order with respect to this compound, and is second order with respect to this ion. Well, here is ion, sorry. Ion, and second order with respect to this H plus ion. That's how we read it. Also, we can say the overall order of the reaction is 1 plus 3, here is 1 plus 3 plus 2. So we have 6. And you say this reaction is 6th order overall. 6th order overall. Most of the time, the useful information is to define the order with respect to every compound or every species. So the reaction, you say the reaction is first order with respect to concentration of H2SeO3. The reaction is third order with respect to concentration of I minus ion. And the reaction is second order with respect to H plus ion. Or you can say the reaction is sixth order overall. All the information you get from here. And also the value of the rate constant is given here. And look at the units of the rate constant. So units are important. We need to write it down. If you know the numerical values, so you include that here. Just don't leave it there. Just plug it in to show the final rate law. And we call this rate law for that reaction. The rate law should show rate equals the value of the rate constant if you know it. If not, just leave it lowercase k, times the concentration of your reactive elevated to the order. If you don't know, just put a letter M times concentration of the second reactive elevated to the order found through the experiment times concentration of the next reactive elevated to the order found experimentally times concentration of the next reactive if you have it, and that's it. Only in terms of reactives. Here we do not include concentration of products. And also we express the rate as a positive number. The exponents in a rate law can be fractional, can be negative, can be even be zero. I mentioned it before, it can be also zero order. So the most common orders are zero order in chemical reactions, zero order, first order, second order, the most common orders for reactions. Third order is possible, but they are very weird reactions going through a third order. You will know the meaning of that order later on. So in general, again, this is how you express the rate law for any chemical reaction in terms only on the products, on reactives. Only in terms of reactives. Here I should write here is concentration of, because the B is the reactive. All right. At least that you had M as another reactive. And how do we find The question is, how do you find these exponents? How do you find the order of the reaction? Using experimental data, we can figure what is the order of the reaction. Let's say we have a reaction A plus B making products. And we know that the rate of that reaction, the rate law for that reaction equals what? Yes, rate constant times concentration of A to a power to a order, and let's call this, usually is M represent any number. This is a standardized way you can say M, you can even say O to the order O or to the order P, any letter that represents any number. And they're found experimentally. It's not common to see concentration of A elevated to the X or Y. Because remember, Z, usually those A, X, and Y are used when they are incognitos, numbers that we don't know. But those exponents, these orders, we know. We must know. We must find these numbers. And that's, I'm going to show you how to find these numbers. So times concentration of B to the power N. Or you can say to the power B or to the power, well, not B, because you can then confuse that with the stoichiometric coefficient. So we choose middle letters. So we don't confuse those with the stoichiometric coefficients. All right. Our job will consist, our mission will consist on finding the orders of the reaction to express the final rate law found experimentally. All right. What is the meaning of this? What is the meaning of the rate law? The meaning of the rate law is as follows. It tells you how the concentration of A affects the speed of the reaction. And also tells you how concentration of B is affecting the speed of the whole reaction. Or how any reactive, concentration of any reactive is affecting the overall speed of the reaction. That is the meaning of the rate law. It tells you how every individual reactive affects the concentration of every individual reactive affects the speed of the reaction. So the whole rate law shows you that, especially the order of the reaction, the order of every particular reactive in the reaction gives you a lot of information. Now, we're going to find this. Now, in this reaction, we have only two reactives, A and B. Therefore, we express the rate in terms of A and B, in terms of concentrations of A and B. Remember, the rate law is represented in terms of change of concentration of A and change of concentration of B over the time. So let's start to analyze, to do critical thinking to find how the concentration of A is affecting the speed of that reaction, is affecting the rate of that reaction. So if we want to know how by changing this concentration will affect the speed, it makes sense that we need to keep this constant for a while. So we need to set different experiments. In one set of experiments, we will make changes on this concentration, keeping this concentration constant. That's the only way to know how, by making these changes, that will make or will affect the rate of the reaction. And then we'll have another set of experiments where we are going to keep this constant and we'll start making changes on this concentration to see how those changes made in the concentration of B produces a change on the rate for the reaction. So here is the experiment. This is actually the experimental results. 5 different experiments, and we are going to play with the concentrations. So remember, we are playing with the concentrations to see how changes made here produces a change on the speed. Increasing concentration of this, can that increase produce a change on the rate? Rate increases, rate decreases? Or start making changes here. Keep this constant, do not move this, do not change this concentration, start making changes here and see how the rate is affected every time you make change in the concentration of this species here. But the only way to know that is keeping this constant. So you want to know how these changes here affects the rate, keep that constant, keep the other constant. So you change only one variable. You keep the other variable constant while you are doing this experiment. And then you switch. Keep this constant, this concentration constant, and make changes here and see how the rate is affected every time you make changes here. And what kind of changes you can make on the concentration? Well, you can double the concentration, you can triple, you can increase concentrations. Try to do it in a proportional way so you can see proportional change of rate. Don't just throw any change, because then it's going to be hard to observe that change here, if any happen. So let's see the numbers. Can you identify here in the first 3 experiments? Let's group these experiments results. Let's group the first 3 experiments. In these 3 first experiments, did you notice what concentration is changing and what is kept constant? Yes, this one is kept constant here. constant. Let me change the symbol because you can get confused with that K we have in the equation. No, what I mean is constant, not changing, not change. During these three, look at here. First experiment, 0.10 moles per liter. That's the concentration of B. Second experiment, the same. Third experiment, the same. No change in the concentration. That means we are keeping this concentration constant during the first three experiments. Here. So we keep this constant, this concentration constant, and then we can make changes here, and then we can observe if there's any change on the rate every time you make changes on A. All right, let's start making changes on A. First experiment, we run the experiment using 0.10 moles per liter of A and using 0.10 moles per liter of B, and the speed of the reaction was measured, 0.20 moles per liter per second. That's the initial rate. How do you measure that rate? There are many different ways to measure. You can measure it in measuring this, following this. You can measure it following this, but this is constant. Or you can measure it following one of the products being formed. That's a different thing. How you measure it, how you measure the speeds. There are different ways. There are different instruments that can be used to follow that reaction, to measure it during different stages of the reaction. So this is our first experiment. Second experiment. This is telling you nothing here. This is just the measurement of the speed of the reaction using this concentration. Now, let's start making changes. What was the change made on the second experiment? Notice that we double the concentration of A. We increase times 2. Times 2. We double this concentration. So we use now 0.20 moles per liter. And then we have that same concentration of B as the first experiment. Remember, those are independent experiments. Two different experiments. In one test tube, you run this one beaker. In a different beaker, on a different tube, under the same temperature, you run a second experiment. So in the second experiment, you use 0.20, which is double that initial experiment. You use 0.10, you did make changes here. And look what happened with the new rate. The rate for the second experiment. It went up by how much? 2x, right? Double. So you say, if I double concentration of A, the speed also doubles. Very interesting. So if this reaction, if this concentration here goes up, this rate goes up too. But that's not enough to say. We need to say by how much. If you double here, the rate also doubles up. Just to make sure, let's do one more experiment in a different beaker, in a different tube. You measure everything again at the same temperature, but this time we are going to increase the concentration of A to 0.30 moles per liter. We use the same concentration of B. We don't want to make changes here because we are analyzing how changes here affect rates here. And what happened? What happened when, by how much we increase here the concentration? From here to there, we increase 3 times. 0.30 is 3 times bigger as 0.10. By how much the speed went up? From 0.20 to 0.60 moles per liters per second. By how much? It went up by 3x2. So how do you call these relationships here? If you double here, here doubles. If you triple here, here triples. The speed triples. How do you call this relationship? You say this is a direct relationship. They are proportional. And you say they are proportional. Direct proportion is something, you double something here and the rate doubles here, so that's proportional. If you increase here the concentration, then you observe an increase on the rate also in the same proportion. Exactly the same proportion. So it's direct. Exactly in the same proportion. It's linear. The increment is linear. When you observe that, you say the concentration of A is proportional, the increments on concentration of A is proportional to the increments in the initial rate at the same proportion. From there, we call this first order. And you say the reaction is first order, yeah, first order. You say the reaction is first order with respect to A. So that's our first part. And you say M, we just found is 1. It's first order. Again, it is first order if the initial rate increases when you increase the concentration of, in this case, reactive A on the same proportion. The increments here and the increments here are on exactly the same proportion. You double here, double here. You double concentration, the rate doubles. If you triple the concentration, the rate increases 3 times, triple. If you increase concentration 4 times, then the rate will increase 4 times, and so on and so forth. That is a description of a first order reaction. And that's the meaning. That's the meaning of first order. And you can replace. Now we know the value of M. M is 1. Let's find the value of N, the order of the reaction with respect to V. How do we achieve that experimentally? Well, we know that we need to keep this constant and make changes on this concentration to see what happens with the rate. We just found that changes on concentration, you change it 2 times, concentration, then the rate will change 2 times. That's first order. Right away, you say that's first order. You don't have to do more experiments. You do one more just in case, but that's it. You see the same rate of increments on both the concentration and the rate. Same rate of increments, same proportion of increments, that's first order. That's the meaning of first order with respect to that reactive A. On the second experiment here, in the second experiment, we have who's constant on the second experiment? This is constant. So this 3, 4, and 5, this is common. Experiment 3 is common to all experiments. So now we are going to analyze 3, 4, and 5. We don't care about what happened here. We already got the information from here, but we are interested to know how changes made on concentration of B will affect the rate of the reaction. In order to know that, we need to keep this constant. So this is not going to affect the results of my experiment. So we keep concentration of A constant in the second round of experiments, experiments 3, 4, and 5. And the first experiment for the second round is experiment number 3. Initially, we put in the container in a beaker 0.30 moles per liter of A and 0.10 moles per liter of B. And they measured the speed of that reaction and they found 0.60. Okay, let's do one more to compare. Right now, we don't know anything. Just that's the initial rate for the first experiment. Second experiment. Remember, we keep this constant. Now we are going to make changes on concentration of B. What kind of change we're making here? What kind of change we are making from here to there? What kind of change on this concentration? We are double. We double here the concentration, so we multiply by 2 the concentration, 2 times. On the experiment number 4, we increase the concentration of B 2 times compared to experiment number 3, concentration. Let's see how that change here affected the speed of that reaction. Here, what happened with the new concentration, new rate? The rate went from 0.60 to 240. By how many times increase? Same proportion? No. It's not the same proportion. If that were the same proportion, will be 2 times, so that will be 1.2. It went up to 1.2 to double. No, it went more than that. By how much? What factor is here? You want to know? Easy way, just divide this number by the previous one. And what do you get? 2.40 divided by 0.60. You find that this number needs to be multiplied 4 times to get this. So this is the factor. Can you do the analysis again? If concentration was double, and that produces a rate to go up 4 times, quadruple. Wow, that's an interesting change. It's different than here. This is in the same proportion. Here, obviously, we don't have the same proportion. From 2x went up to 4x. So basically, we can say that from here, from 2x went up to 4x. So it went up by 2 squared. Let's do one more experiment just to make sure. There, experiment number 5. We keep these concentrations constant. Let's make change here. Let's increase from 0.10 to 0.30. So we are multiplying the concentration 3 times. We're increasing this concentration of B 3 times from here to there. Let's see how this change affected the speed of the reaction. So the speed of the reaction went from 0.60 up to 540. How much is that change? How many times? 9 times, right? Increases 9 times. It went up, the speed of the reaction went faster 9 times than the initial. You triple here, if you triple the concentration of B, the speed went up by a factor of 9x. So the change was 3x in concentration and 9x in speed. So 9 is 3 squared, right? 3 times 3 is 3 squared. And from here, our conclusion is the reaction is second order. The reaction is second order. Therefore, the exponent on B, the exponent of B in the Rayleigh law, which is the letter N we were using, is 2, second order. You say second order. And that's how you find the orders of the reaction. Using experimental data, then you put it on a table like this, and then you do the analysis, exactly the same way I did it. Which is really easy. Keep one constant, make changes on one of the reactives. Double the concentration in that reactive, you're making changes. Keeping the other one constant. See what happens with the speed. If the speed goes up at the same proportion, then is first order. If you double concentration and the speed goes up quadruple 4 times, then it's second order. That's it. That's it. What about if you make changes here? What about if you make changes here, you keep this constant, and then you see no change at all on the speed? No change. On the right means 0 order. That's it. 0 order. Like For example, we can have a reaction. We can have a reaction A plus B plus C forming products. So the rate law for that reaction will be equilibrium constant. Sorry, not equilibrium. Rate constant is lowercase times concentration of A to M times concentration of B to the N times concentration of C to the P. That will be the right expression for the rate law for the reaction. So you can say, okay, rate for that. Once you find the orders, you can replace the orders. And you say, for this, let's suppose we have this reaction. So now we know the rate equals, rate equals constant times concentration of A. And what is the order we found for A? Is first order. It's first order. We don't have to write it, just leave it that way. Times concentration of B. We just found the order for this reaction using these experimental results, and we found the order with respect to B is 2. But let's say we have another experiment with C. We keep A constant, we keep B constant, concentration of B constant. We just change concentration of C. We double concentration of C. See what happened with concentration with the rate and not change. So you say, oh, that's zero order with respect to C. So you will say concentration of C is zero order. That you write it. But also you can simplify. Because what is a number to the exponent 0? Number A to the exponent 0 equals what? 1. So you can rewrite the rate law and you say the rate for the reaction equals constant times concentration of A times concentration of B squared. That's it. And you have 3 reactives. This is first order here, first order, that's 1. We don't need to write it. With respect to B is second order, and it's not showing C, that's times 1. Although C is here in the reactives in your equation. That means it's 0 order with respect to that. In other words, by changing concentration of this reactive in that reaction, we will not make changes on the speed of the reaction. Also, the way we analyze this, the way we understand this is telling you that since this is first order, it's telling you, all right, every time you double this concentration, the speed will double. That's first order. And here, with respect to B, is second order. So it's telling you, every time you double the concentration of B, the speed of the reaction will quadruple. That is what it's telling you. And from here, you can find the overall order, which is 1 plus 2, and you say it's overall third order. third order. Doesn't give you a lot of information. It's more important to know what is the order of the reaction with respect to each reactive. Again, the most commons are zero order, first order, second order. Very rare reaction goes third order. And that's this next meaning. There's another meaning for the order of the reaction. And that meaning has to be with something that we call molecularity. Molecularity of the reaction means how many molecules are participating during the transition state on the kinetics for that reaction. So for first order, you say first order. For first order, the molecularity is 1. That's the molecularity, 1 for first order. So the order is giving you 2 pieces of information. 1, how the concentration of reactive A affects the speed. So you say it's first order, therefore that means when you double concentration of A, speed doubles too. That's the first meaning. And the second meaning is the molecularity. Also tells you that during the transition state of the kinetic of that reaction, only 1 molecule is present there or participate during that transition state in the activated complex. We'll discuss that later when we go through mechanism. So, and the second one, we'll recall this later. For the second order, the molecularity for second order reactions is 2. So 2 meanings. When they say the second order means every time you double the concentration of B, the speed will quadruple. That's second order. And the second meaning of second order is that the molecularity is 2. In other words, 2 molecules participate in the activated complex during the transition state of the reaction. And the other important one is zero order. Zero order, they are not affecting the reaction, the speed of the reaction. That's why they don't show up here. Zero order, and the molecularity therefore is 0. So these 2 important, you remember these 2, that will be important, especially when you go to organic chemistry. It's going to be really important to know this concept, the relationship between the rate law, the order of the reaction, and the molecularity of the transition state. It's very useful in organic chemistry, especially when you are writing and studying reaction mechanisms. Here, I give you another way to calculate the orders of the reaction. I think the analytical way is a lot easier. Just look at the numbers. Look at the numbers. You say, okay, concentration doubles, speed doubles, first order, right away. And then you look the other set, and you say concentration double, and speed quadruple, second order, right away. That's it. Or you can say, okay, concentration doubles and speed no change is the same. So that means zero order. So that means that particular compound is not affecting the speed of the reaction. You can make changes on concentration of that reactive, and that is not going to make changes in the speed of the reaction. All right, that's how you write the rate laws, and that's how you find the order of the reaction, and that's how you do critical thinking, analyze information from that rate law. So once we know the rate law, we can find the rate constant. Let me show you how to write it. We have not finished writing the rate law for that particular reaction. We just found the values of M and N using experimental data. But let's find something, we need to find something else here. What is missing? We know this, here the rates. We know concentrations of A, they are here. We know concentration of B, they are here. We know M, we just found is 1. We know N, we just found is 2 here. What is missing? What else we need to find? Yes. This one. The rate constant. But that's the last thing you need to do. First, you need to find M and N. We just found them. So we can write, so now we can write partial answer for that. So you say the rate here equals K times concentration of A to the first exponent times concentration of B squared. So first order and second order with respect to B. We already know these values, these numbers. Now we can find this one because we already know this, we know this, we know this, and we know the exponents. And that's easy because we have all the information we need. So from here, we are going to solve for K. So K will be rate. We need to leave this alone. So I'm moving this. This is multiplying here. So it goes down here to divide. But some people likes to say, okay, divide everything by this expression. I just like to move here. If something is multiplying here on this side of the equation, just send it there to divide. So it's going to be rate over concentration of A times concentration of B squared. We just plug in. We can plug in because we already have the numbers. And which one? We have 5 experiments. Which one you want to plug? You can choose. Pick and choose. Any of those experiments. You can use any of those experiments to values to plug into the equation. I personally want to choose first experiment. This one. I'm going to use these values. experimental values to find the rate constant. Why I'm again, you can choose any of those. You can pick any of those experiments. 1, 2, 3, 4, or 5. I personally want to choose experiment number 1. Why? It's the easiest. Look at the numbers, 0.1, 0.1, 0.2, the easiest. You can do even in your head. You do this 0.3, 0.5, 5.40, a little bit more complicated. So we need to try to make things easier. So let's plug in that number. What is the rate on experiment number 1? Is 0.20. 0.20. What is the concentration of A on the experiment number 1? Is 0.10. 0.10 times concentration of B, which is 0.10 also, 0.10 square. Now we know the exponents, and that's what we are going to use here. This is first exponent, this is second power here, square. So if we do that, we'll have 0.20 divided by 0.10 times 0.10 squared. How much is 0.10 squared? I believe 0.010 times 0.10 is going to be 0.0010. And the rate will be, when you do that division, will be, so it's going to be on the bottom, 1.0 times 10 to the negative 3. When we do the operation, this number divided by this is going to be 0.20 times 10 to the third. You bring it to a scientific notation, it's going to be 2.0 times 10 to the second. That's what we got here. Yeah. You see? 0.2 to the second. So you do the operation there. That's what I asked you at the beginning. Please stop the recording and go and review with your little brother, your little sister, this basic elementary math. So you can do this very quickly, these calculations. And that's the numerical value. I mentioned it, that we need to express also the units of the rate constant. How do you work the unit? I like to work into, to separate both calculations. I do the numerical calculation first, and then I do separately the calculation of the units. I like to work the units independently. So let me show you this. We just did it, the numerical value, how to do the numerical value of K. Look, show you back here. This is what I did. Just plug in the numbers only, not the units, because I like to do it separate, right? So this number here ended up being 2.0 times 10 to the second. But we are missing the units. And I like to do that separately. So I do the units of K. I just plug units equals. What is the unit of here? This is the equation from here. This is the equation of for the rate constant. So let's plug. First I plug numbers. Now I'm going to plug only units. What is the units of rate? Here is given here on top. So on top goes moles per liter, that's moles, liters, -1 per second. That is seconds, -1. Those are the units of the rate. Now on the bottom, what do we have? We have concentration of A. What is the unit of concentration of A? Moles per liter. So that's going to be moles, liters, -1. That's the first one. I like to separate those so we don't get confused later. Times concentration of B squared. So the units of concentration of B is the moles per liter. So it's going to be moles, liters, -1 square. And once you write everything down according with the rate constant equation you get here from the rate law, we can simplify. How do you simplify this? Look, this term here. Look, this term here is the same, moles, liters, -1, same as this, moles, -1. Right, so we can cancel this. Cancel this part of the expression with this one. We just simplify and we ended up having seconds, -1 over moles, liters, and we multiply. So this is moles per liter square. So it's going to be moles square times liters this is moles per liter or moles liters -1 square. So that's going to be moles square liters -2. Now we can bring everything up, put everything on the same line. So you will say moles, since it's positive on the bottom, goes up negative, right? So this moles -2 times liters, that was negative, now it's going to be positive, liters second, positive, times, we just leave this, is already on top, seconds, -1. We try to put on the same, in this order, first moles, then liters, then seconds, because that makes sense, because the units of rate are moles per liter per second. This, when you see this expression here, and every rate has different units because it depends on the stoichiometry and depends on the order of the reaction. In general, it's going to be something like this. And they have meaning and they're important. They have no meaning really, but they are important because when you plug into the equation, it will help to cancel out the other units in order to get the rate. Remember, the rate of the reaction has to be moles per liter per second. That's the rate of the reaction. Moles per liter per second. Change of concentration over change of time. That's the rate of the reaction. So these units here will help to cancel the units here, because then you will have here moles times moles square liters -2, and at the end you need to end up with just moles per liter per second, and the constant units of constant will help you to bring everything down to the correct units. for the rate law. All right, so this is how you write the rate law. That's the most important thing you learned today. How to write the rate law, how to do interpretation of the orders of the reaction, how to find the orders of the reaction from experimental data. The second meaning of the order of the reaction, which is the molecularity. I didn't go deep on this because later we're going to use this information when we write reaction mechanisms. We learn how to use, how to write the rates of reactions. We found the relationship between the stoichiometry and the rate on the reaction. And I put this slide here to do a little bit of review on natural logs, ln. It should be written like this, natural log, ln, this way. And the other type of logs is this, which is base 10. So this is base 10, and this is base E, number E. So for you to review, plus the review you are doing already, again, stop here, go back, talk to your little sister, your little brother, your cousin, your niece, or your uncle, or your big brother, your big sister, or your wife, or your husband. Talk to somebody. But just sit down yourself with the textbook, or find stuff on the website, just basic stuff. We're not going to get crazy. But this basic stuff, if you don't know it, it's going to make your life harder. So solve the problem right now because we are going to use it. The next, again, so remember, the rate laws will help us to write reaction mechanism. That's why we are studying the rate laws now. The second part is to express a different type of equations. Let me write that down here because it's important to keep focus on why we are doing things and what is our goal. So the rate law that we just learned, rate law, or rate laws, because we have first order, second order, third order, will help us to write reaction mechanisms. Rate laws will not help us to make predictions in the chemical reaction. Why is that? Look at the chip of the rate law. Oh, I didn't finish it, sorry. Once you know the equilibrium constant, once you know, sorry, not equilibrium constant, again, it's my fault. Rate constant. Once you find the rate constant, now we need to express the complete rate law. I didn't do that. Wow, I'm losing credits here. So rate equals, now we write everything down. 2.0 times 10 to the second moles, -2 liters square. I prefer this order, not that order. Seconds -1 times concentration of A times concentration of B square. And that's it. That's the final answer. Everything is there. We found the equilibrium. So again, oh my God. Rate constant with its units. We found the order of reaction with respect to A, which is first order. We found the order of B, which is second order. And now we have a complete rate law for that reaction. So that's how you express it. But again, we can not use this equation here to make predictions in the chemical reaction. For example, if the reaction consumes 0.1 mole of A, the particular reaction, according with this experimental data, if the reaction consumes A at the rate of 0.10 moles per liter per second, how much will you get after 10 seconds? How much of B will you get after 10 seconds? Or how much left over is going to be of A after 10 seconds? Can you use this equation to do that? No, right? Well, we have to work it out to make it work, and that's what we're going to do. But right now, no. Why not? Do you see the time somewhere here? No, I don't see the time here. Time is not included here, only here, on the rate constant. But this equation is not written in function of time, as a function of time. So we cannot use this to make predictions. We need to convert this, we need to work it out in a different way. So that is going to be expressed as a function of time. And then we can use that to make predictions. That's why the next is to learn how to write derivative Rayleigh laws or integrated Rayleigh laws. And that's going to be our next next conversation here, next video. I'm going to stop here and we'll continue on the second part of this chapter, which is going to become more and more interesting. All right, stay tuned. See you next time.